Thank you, Halil. And thanks, Isabel, for inviting me to this great conference. And I was very happy to learn more about the MiRoR consortium and the projects involved, and also being in this venerable institution. So today I'll be talking about transparency of clinical research publications and how natural language processing can contribute to assessing and improving it. Let me start with a short overview of my talk. First, I will basically talk about some basic background on the use of natural language processing for enhancing research transparency. Then I will talk about some recent research that I've conducted in this area. First, I will talk about assessing clinical trial publications for adherence to reporting guidelines. And I will close with talking about some meta-research investigations that we did, which involved natural language processing. First, research transparency and the role of NLP. A lot of the speakers already talked about reproducibility crisis, and I'm not going to really go into much detail about that, but it's a big problem in biomedical research, mainly due to the size of the research investment. There are many causes, some of which have already been discussed, and increasingly there are more interventions to address the problems and improve the state of affairs, including standards and guidelines, as well as cyber infrastructure, such as computational notebooks or workflow systems. Reproducibility is a very umbrella term that's being used, but my talk and my research is mainly on research transparency, which can be defined as reporting of methods and materials in a manner that provides enough information for independent assessment and reproduction. And there are some other related notions, such as rigor, integrity, which are broader terms. Rigor having to do with, both of them having to do with research conduct and reporting, rigor more focusing on robust and unbiased research conduct and reporting, and integrity having to do more with honesty and verifiability. These are distinct from other terms such as reproducibility, replicability, and translatability, or sometimes called generalizability, which have more to do with the application of results or findings of earlier research. So my talk will not really go into going into these, except at the end I will talk briefly about translatability. So what does NLP have to do with this? Or first of all, what is NLP? Or what is bioNLP as NLP applied to biomedical domain? The main goal here is to transform natural text, free text, into that exist in, for example, scientific publications, clinical notes, or drug labels, into computable representations so that they can be processed at large scale in order to support knowledge discovery and clinical decision-making applications. BioNLP shares tools and techniques for the open domain NLP, which is NLP as applied to general English or other languages. But arguably, there's been a heavier emphasis on knowledge representation, ontologies, and corpus annotation, in other words, resource development. And with the availability of resources, increasing availability of resources, some tasks, some NLP tasks, such as text classification or entity recognition, there's been substantial progress in these areas. And how can bioNLP help research transparency? I started with observing the fact that textual artifacts are core to the biomedical communication lifecycle. It involves, as well as scientific publications, it also involves grant proposals, manuscripts, and protocols as well. And some meta-research studies focus on transparency, but most of the analysis that's done in those studies are manual, which is time-consuming and labor-intensive. The main advantage of NLP is providing scalability. So you can assess these artifacts at large scale, assuming that you have methods that are accurate enough. To be more specific, it can help us scrutinize reports of conducted research so that they can be reported more completely and accurately if you look at manuscripts. And it can also help us manage published literature more effectively if we have tools for literature surveillance or evidence synthesis. And it can improve quality of proposed research in this way, helping us reduce research waste. In doing so, it can complement efforts in standardization and guideline development. Now let me talk about my own research on this area. First, clinical research, clinical trial publications, and reporting guideline adherence. This is a preliminary study, and our overarching goal is to develop text mining methods to automatically recognize CONSORT checklist items in randomized controlled trial reports. In this preliminary study, this preliminary study consisted of basically an annotation study and also comparison of baseline rule-based and weakly supervised machine learning methods to recognize CONSORT checklist items. As many of you already know, reporting guidelines have been proposed to promote transparent, complete, and accurate reporting in biomedical research. And many have been developed under the umbrella of Equator Network, CONSORT for randomized controlled trials, ARRIVE for preclinical animal studies, and STROBE for observational studies, for example. And it has been shown to improve reporting transparency, and with increased transparency, it might be possible to reproduce these studies more easily. However, many systematic studies, systematic reviews done in this area shows that adherence remains inadequate even in journals that endorse CONSORT guidelines or reporting guidelines in general. CONSORT Statement is, as I said, reporting guidelines for randomized controlled trials, consist of a 25-item checklist and a flow diagram. It has been endorsed by over 600 journals, and it's the most commonly, most well-known reporting guidelines, endorsed by many high-impact journals, and some extensions have been developed for CONSORT. Just to show some CONSORT examples, this list shows 5 checklist items. The second one, for example, is allocation concealment, checklist item number 9. What this table is telling us that it's expected to be reported in the method section, and on the rightmost column, we see a sentence that discusses this particular checklist item. The goal of our study, general goal, is to develop text mining methods which can locate key statements corresponding to these CONSORT checklist items in a manuscript or a publication, and to give alerts in their absence. So we're basically envisioning a human-in-the-loop type of system. Such a tool can benefit journal editors, peer reviewers, authors, and systematic reviewers who are either reviewing these articles or manuscripts, authors who are writing, so we can point out issues in their reporting, and systematic reviewers who are trying to find the best, most rigorous studies for a given research question. There are some commercial and academic software for some of the items, Penelope, Stat Reviewer, etc. But as far as I know, there's no tool that looks at reporting guidelines per se. In order to develop NLP methods, we need a lot of label data. So in order to do that, we annotated some data. We used Cochrane's RCT search strategy to sample 50 articles published in 11 journals, 9 of which were CONSORT endorsing, published since 2011. And we did some basic pre-processing to split sentences and extract sections from these articles. We then performed a sentence-level annotation where we annotated each sentence with one or more CONSORT checklist item or none, if none is discussed in the sentence. 25 checklist items corresponded to 37 fine-grade categories, since some of the checklist items consist of A and B categories. 6 annotators were involved, people who all have some expertise, some understanding of biomedical research methodology. And as I said, we annotated 50 articles. One was an exploratory annotation. 30 were double annotated by 2 annotators and then adjudicated by a third. And 19 articles were single annotated and then corrected by a adjudicator. And we developed guidelines throughout this process, and we used a web-based tool that we developed in-house. So some corpus statistics, 50 articles. We annotated more than 10,000 sentences from these 50 articles. And about 45% of the sentences had some CONSORT item discussion. And the number of annotations were more than 5,600, meaning each sentence was annotated with more than 1.2 annotations. And the mean number of items per article was 27.5, and then the highest was 35, and we actually found that this was the only article that was fully CONSORT compliant. The highest number of CONSORT items per sentence was 5, and this is that sentence, which, as you can see, is very dense with information. So we found that out of 50 articles, 40 or 80% of them had more than 80% of the more than half of the CONSORT checklist items annotated. And this is color-coded by the sections. So broad items such as background or outcome results were annotated in all articles, whereas items that indicated some change to the trial, for example, changes to trial design or changes to outcomes, were annotated in a few articles only. Among the rest, protocol access was annotated the least, so we thought that was interesting. And some items were discussed over many sentences, such as outcomes or outcome results or interpretation. We found that CONSORT defines these items very broadly. So in outcomes, we're not only extracting sentences with primary or secondary outcomes, but also how and when they were assessed. So we performed inter-annotator agreement calculation using a measure called MASI, which took into account multi-label annotation. We found that agreement was about 0.6 by article. And between annotators, the agreement was also around 0.6, changing, the range was 0.58 to 0.64. And by section, we found that items in the other CONSORT section, meaning things like trial registration or funding, we had the best agreement on, understandably, whereas the agreement was lowest in results section, and methods and discussion were relatively similar, about 0.59, but we had more variability in agreement on the discussion section. We also looked at inter-annotator agreement by CONSORT item, and not surprisingly, trial registration is what we agreed on most, and it's the simplest thing to annotate. We also found that we had good agreement on sample size determination. In terms of the lowest agreement, we found that that was with numbers analyzed, which sometimes were reported in figures, and we weren't consistent about annotating figure captions in this case. So we also did some natural language processing experiments, baseline experiments, and we only applied these to method sections or method section relevant items. The rationale here was that these were most relevant for replication and rigor of the study. So we developed a few rule-based methods. In order to do this, we downloaded a large set of clinical trial reports, about 15,000 clinical trial publications, and we did an automatic analysis of frequent subsection header and phrases. So we found some predictive phrases and section headers. For example, the phrase mask the treatment was taken to indicate blinding procedure item. And if a subsection header in the method section had change and plan at the title, we took that to all the sentences in that section to indicate changes to trial design. We compared these methods to a neural network-based method called ULM-FIT, which is one of the recently popular contextualized language model machine learning tools. And the idea here is that it comes with a pre-trained model that has been trained on a very large corpus, in this case Wikipedia text of about 100 million tokens. And this is then fine-tuned on the training corpus for the task that we are trying to address. Since our data set was relatively small for machine learning, we tried to generate training data automatically. And we used 4 methods, basically, and we looked at their output, and we only took sentences that all these 4 methods agreed on as our training data. These methods were phrase-based and subsection header-based methods that I just discussed, as well as predictions from robot reviewer tool, which extracts eligibility criteria, interventions, and outcomes, and also cosine similarity with the sentences that were in the CONSORT documents. We trained on this data, and we validated and tested it on the manually annotated data set that we generated. The preliminary evaluation results at the checklist item, we calculated macro evaluation metrics, meaning the rare items were basically considered to have the same importance as really common items. And in this case, we found that simple phrase-based method basically gave us the best precision, 0.54, whereas the ULM-FIT deep learning-based method gave us better recall and F1 score, which is the harmonic mean of the precision and recall measures, although the difference was not very big. And at the article level, we looked at whether the CONSORT item was present, was predicted to be present in the article or not. And in this case, the results are higher. We're more successful with this, but the trend is similar. Phrase-based method gives us highest precision, whereas recall and F1 score is better with ULM-FIT, even though the differences are relatively minor. Looking at the CONSORT items individually, we find that ULM-FIT method basically does well when we have a lot of data corresponding to that item. For example, in outcomes and eligibility criteria and blinding procedure, for example. Whereas it fails, essentially, at items that have very few examples, such as changes to outcomes where we got 0% accuracy. Whereas phrase-based method does relatively well overall. So in conclusion, we found that annotating CONSORT items in full articles was a very cognitively challenging task with 37 fine-grained categories. And the inter-annotator agreement varied significantly from 0.06 to 0.96. We found that some items are defined very broadly, for example, interpretation. So annotators were generally sometimes confused about whether they should annotate it or not, because it turned out like half of the discussion was annotated with this label. And some items are relatively similar, and it was hard for the annotator to distinguish between these, such as outcome result versus binary outcome result versus ancillary analyses. However, the manual annotated corpus, we feel, can be used as a benchmark, and we plan to do more work on this. And we found that very simple baseline methods that we used gave moderate results. So there's much room for improvement for this. So now let me move to the last part of my talk, where I'm going to talk about how we used natural language processing in support of meta-research, to answer some meta-research questions. In the first one, we looked at peer review and spin, basically. Spin is a concept developed by Isabel. And we looked at two types of spin. The first one is the failure to acknowledge the limitations of a study, and the second one is inappropriate overstatement of claims. Our hypothesis was that in peer review, before peer review, a manuscript would discuss fewer limitations and make stronger claims, and after peer review, they would have more limitations and they would temper their claims as a result of peer review. So our approach was to use existing NLP methods that I developed earlier and apply them to discussion sections of manuscript and publication pairs. The method to recognize limitations is recognize limitation sentences with an accuracy of 91.5% accuracy, and has been recently published. And for overstatement of claims, we looked at the notion of hedging, which is a rhetorical device that's often used in scientific publications to soften claims, and involves the use of phrases like, or words like may, suggest, etc. So what the tool does is basically it calculates a hedging score for each sentence and measures and this score is a measure of how speculative that sentence is. And the tool was applied to in an intrinsic evaluation. We found that tool was 95% accurate in identifying speculative sentences. And we applied this approach to over 400 randomized controlled trial reports from BMJ Open and 27 BMC journals. The commonality between these is that they all have open peer review policy. I'll just briefly talk about the results. We found that limitation reporting increased by 57% in peer review, but in absolute terms, this is not a lot because it corresponds to 2.5 sentences in manuscripts on average to increase to 3.87 sentences in publications. We found that there was a greater impact on manuscripts with zero or low number of limitation sentences. And we also found that in manuscripts, about 45% did not have any limitations at all, whereas this was 33% in publications. But we didn't find any support for the hypothesis that peer review would increase hedging of claims, because authors are sometimes asked to temper claims, sometimes they're asked to write in more certain terms. Finally, translatability of animal studies. This is another study that we did. And the motivation here was that despite tremendous investment, no disease-altering therapies for the common neurodegenerative diseases are available for diseases such as Parkinson or Alzheimer. And this is in stark contrast with promising results that are shown in animal models for the same conditions. So our approach was to basically assess the therapeutic approaches in the context of characteristics that can affect translatability, such as species, models, molecular targets that are engaged, and outcomes that are reported. And we wanted to apply this to a large-scale analysis to reveal patterns of animal use. Our case study was Parkinson's study, and we used text mining approach that involved off-the-shelf NLP tools such as MetaMap and GNorm Plus developed at NLM. We've augmented these with list rules and supervised machine learning to extract interventions, species, models, molecular targets, study outcomes, and functional outcome measures from publication abstracts. We did an intrinsic evaluation study that involved about 500 abstracts, And then once we validated it on this annotated data set, we performed a large-scale trend analysis on 3-year data, about 15,000 abstract. The idea was to sort of do a combinatorial analysis of the terms that are extracted by these modules. So we can basically look at mouse studies that were conducted on genetically altered mice, and where the study outcome was promising. We found that this is just basically showing therapeutic intervention trends for Parkinson's disease, and our studies confirmed that alpha-synuclein, which is most commonly targeted molecular target, and L-DOPA, levodopa being the most commonly used pharmacologic intervention. And we were also able to look at how we were also able to integrate information from different modules. This shows that, for example, with L-DOPA, outcome was stated to be promising in about 2/3 of the studies, whereas this was less than about half with alpha-synuclein, and functional outcome measures were reported in most of the levodopa studies, whereas it was only reported in about 1/4 of studies for alpha-synuclein. So in concluding remarks, I feel that NLP and text mining can aid in assessing and improving research practices, but many challenges lie ahead. And these include things like availability of full-text articles, where most of the rigor, integrity, and transparency problems are manifested, but we have very little access to these currently. And most of the NLP methods require annotated corpora, and this requires a lot of expertise and time, and it's really hard to find such expertise. And some relevant information for transparency or rigor are basically in tables and supplementary material or figures, and NLP, there's currently very little NLP work on these. And finally, our methods need to be accurate for the community to adopt these tools, but I think we're getting there. Thank you.
Thank you. So we can take a few questions now. Please.
Thank you for your talk. I really like these automated methods. I was wondering if you're going to share the analysis code. And the reason I'm asking is also because you mentioned Stat Reviewer and Penelope, and I've looked into those a little bit. And yeah, I had to stop almost immediately because there's absolutely no information about these things available, which means that I don't know whether I can trust them. So yeah, long story short, are you going to share the code that you're using?
That's the goal. I mean, the methods are not accurate enough at this point for us to, I mean, we're planning to share the data that we annotated, certainly, but our methods are not currently accurate enough to be used in in production mode, but we hope to get there.
Hi, thank you for your talk. Katie Drax from the University of Bristol. I'd like to add a +1 to that because I'd love to do the same thing with the strobe checklist. But this is quite a specific question, but with the CONSORT statement, when you were looking at article type, so you're assessing the reporting quality at article level, was there ever a case when an article contained several studies and that it might have been worth doing the reporting checklist at sort of a study level?
I'm not sure I understood the question. Can you?
So if an article contains multiple studies...
Oh, okay. We actually excluded those.
Oh, okay. How many of those did you find?
I'm not sure I have the number on top of my head, but these 50 were basically single studies.
Okay.
Well, actually, I have a question for myself, for the audience as well as Halil. So it seems that one way that this kind of NLP methods could be used in practice by researchers is by having some kind of plugin, like when you're writing an article, and it would go and highlight the sentences in your article that meet the requirement from the guidelines. So I guess the question for everyone is, do you think that kind of thing would be useful? And the question for Halil is, Do you think that this is something that could be easily done based on the research you've conducted so far? And could it also be a way of sort of crowdsourcing some annotations from users of the plugin who could validate the sentence suggestions made by the tool?
I think that's a possibility. But we have to basically see whether we could do that. But yeah, I mean, I'm thinking, I just kind of showing you the preliminary study, really. It's not quite, as I said, it's not really in production mode. But the ultimate goal is for us to use this as a sort of author assistant tool in some way, but also help as a sort of assistant for journal editors or peer reviewers as well, so that at least they can get a first sort of, before even reading the article, they can sort of see some highlights about what the possible problems could be with the paper.
So if we had such a plugin available, like how many of you would use it? Some would try. And some
Of course.
Okay. Well, thank you, Halil.
Thank you.